All right, so we're here for temporal anti-aliasing with neural networks, obviously. Work that I did at the KIT Institute in Germany with Max and Carsten. You know aliasing, what we get when we do rasterization or ray tracing, the jaggies, they're everywhere they're always there when we are doing rendering, which means that anti-aliasing is also mostly everywhere. So anti-aliasing is common, and we want to have a good one. And we know that there is more data to be gained in the frames that we've just rendered. We just spent budget on it. So previous frame are more data, but some of it is good data. And temporal anti-aliasing has a problem, which is you need to get rid of the bad data and keep only the good one. And this is difficult. And at some point, temporal anti-aliasing becomes some of a college of strategy, which are somehow a little arbitrary at some point, and they do get some correct results, and it's decent, but it feels like it's asking more questions than it's actually giving a good answer to the initial problem. So we had the idea that deep learning can just replace all the arbitrary stuff that we're doing and keep the good stuff that we have been doing for a while. So let's just see the pipelines real quick so that we can be on the same page. So on the left, you have the input, you have your anti-aliasing algorithm, and then you have an output. Simple enough. Then for temporal anti-aliasing, you need more frames. So you have a bunch of frames, you use your temporal anti-aliasing algorithm, and you get an output. And usually, to use this data correctly, because of course your camera has moved in between, you use motion vectors. So you have a motion vector that tells you how to go from each of these frames to another. And what you do is you move the previous pixels to the position indicated by the motion vectors, which gives you a new frame that is hopefully more interesting and more useful than the previous one. But that is still a lot of data. You don't use that in runtime, right? That's a lot of buffers, and you probably want to add the depth somewhere. That's too many buffers. So what we usually do, this is good for training, but for inference time, for runtime, it's not really good. So we instead use another approach. We take the current frame, which is the aliased frame, and the previous frame that we have already processed, and the motion vectors between the two. Then the temporal anti-aliasing algorithm produces its output, which is fed back to the next iteration. It's much lighter, much more suitable for runtime. But I'm sure you already know most of this, just for us to be on the same page. So let's see what we have hidden in this TAA blue box. So as I said, we have our motion vector and our previous output, which we will project. This is one part of our input, which also contains the current frame and the depth. And we also feed it a hidden state. So it's basically a storage unit for the network to remember things and to communicate to the next iteration. All this becomes the input, which has the size of your frame, plus so the 3 channels of the input RGB, the depth, the reprojected RGB, and n layers of the hidden state. We did a few experiments that you can see in the paper, where we tried different hidden state channels count, and 5 we found was a good amount, and it depends a lot on how much different kinds of inputs you have. If you want to add more than input RGB, depth, and reprojected, if you add some more, it's also better to have more hidden state. So the hidden state is produced by our network in this way. So you have here the convolutional neural networks. So 3 by 3 is the size of the kernel, and 6 here is the size of the output of the kernel, so it's number of channels. This number also, we tried a bunch of different numbers, and 6 is on the lower end, and 12 is above 12. We didn't see any more improvement. in quality. So we have these three main CNNs, and it branches out here with just one that allows the network to remember things. Of course, networks don't remember things, but it stores at least some data for later, and we're going to talk about what's inside this hidden state. So these are very dark. But you see on the right, maybe, basically the networks comes up with this. We didn't tell it to do anything specific. This is what it chooses to remember for the next frame. And I've looked at a lot of different ones. They are very different. And they are basically all variations of common filters, like, thank you, that's very nice. Like edge detection filters, you have dilation filters, you have thresholds, and it's a combination of all of these. So yeah, I've indicated at the bottom that we use 5 channels of these, and we did not notice any improvement beyond that. So let's go back to our architecture. The core of our technique is the kernel prediction. So we have a 5x5 CNN again, but this time with a 50-layer output. So this is pretty big. And this is because it's 2 kernels of 5x5, basically. We are trying to predict 2 5x5 kernels. So we apply then these 2 5x5 kernels to our current frame, the aliased one, and our reprojected previous output frame. So you can see here how it do that. It's basically just an operation where each pixel gets its own kernel, and we just apply the kernels on the image. Very simple. We sum them, and that's our output. We experimented with more kernels and different variants of the current frame, reprojected, etc. For instance, we also tried with the non-reprojected previous frame, but this actually led to artifacts. And you can think, why are we doing this? This sounds kind of odd, like a convoluted way to get what you want. But one very big benefit is the network can absolutely not dream up things, because it's only using data that's already there somewhere. And this is a big advantage, because as we know, networks tend to dream up things. Also, this is the configuration that yielded the best bang for your buck, basically, in terms of memory and computing cost. So there's one thing we didn't talk about yet. It's that we have different sets of weights for our network. So each layer basically is a learnable set of weights. And we rotate them because we have our renderer that also has something that rotates. It's the Halton sequence in your, basically it's where you aim your ray, when you're ray tracing, you aim your ray inside the pixel somewhere, and it's better to rotate this place so that you can have more data and more variety in your data. And we noticed that there is a significant improvement when we also match this strategy with our kernel prediction. And you can see it here. On the left, we have the exact same network, but one has no rotating jitter sets of weights, and on the right, you do. So you can see a significant improvement there. We have also more variants of which layers we rotate, and you can see that in our paper. So we have our architecture now. Let's see the training data. We have 3 scenes, from the left to right: cafeteria, stairs, and seaside living room. It's more or less realistic camera path with faster, slower movement, and sometimes going through walls, as users often do. So we have a bit more than 500 frames. It's a fairly small resolution, 640 by 480. It's because we need a reference, and the reference is basically we render a very big frame and we downsample it. And so I'll tell you about this a bit later. For each scene, we have a supplemental video, which covers all the comparisons, if you are interested. So during the training, we have randomized patches of 128 by 128 pixels. We have batches of 24, so it's just enough to fill our NVIDIA Titan V. And we use the non-stateful approach, so the big one. This is because it's faster, basically, to train using the non-stateful approach. So the one with all the frames at once and all the motion vectors. We also perform data augmentation. So here we use only channel switching. So it's basically we rotate each channel. RGB becomes BRG or whatever. And it's additional entropy for the network. Even without the data augmentation, we have more than 80 million training samples. So arguably, we can't define that as an epoch. So we had to define it arbitrarily. And we decided that 1,600 patches processed, it's about 2 minutes, and that's our epoch. We usually take 400 epochs for research and validating networks, etc., and 800 for presenting final results. So yeah, how did we get the training done? Of course, we need the reference, and as I said, since we have only reference from 2560 by 1920, we didn't want to resize it too big, otherwise we would not have a great reference. If we would have 8K, we could probably go 1080p. But it works very well already, so it seems like it's not necessary. I'm sure we can go even higher in quality if we have a better, higher resolution reference. We downsample it. We resize it, sorry, with this filter here that you can see that I shamelessly stole from Wikipedia. And to train, we need an estimate of how well the network performed. This is indicated by losses, and all our losses are pixel-wise, so they work on individual pixels. We have first the reference loss, how different the output is from the reference, the gradient loss, which is the same, but for the gradient in x and y directions, and the temporal loss, which is arguably the most interesting one. It's how much there is temporal change between the output, the current frame, and the next frame, compared to how much there is a difference between the reference current frame and next frame. How are these losses exactly computed? It's very simple. It's output minus reference, gradient on x of output minus gradient on x of reference, etc. And you add the gradient in y. And the temporal loss is the interesting one again. So we define the difference between one frame and the next. We define it as a temporal gradient. And you simply do the gradient of the output minus the gradient of the reference. This is by far the most important loss. And the thing is, they have different ranges. So if you compute a gradient, it's not going to have the same range as a simple difference between two images. So we need a coefficient for each loss. That's what we use to adjust the relative importance of each of these losses. And we also use a mask, which allows us to target specifically the regions that have more aliasing. So you can see how we do that here. It's just a simple operation. You can find more details of that in the paper. So we also have a coefficient to select more aggressively the aliased versions, the aliased regions. We found that it doesn't matter that much, and 0.65, so it's a ratio, it's not 0.5, which would be 50-50. We favor a little bit the alias regions, but apparently it works well on anyway, except if you go for very high or low values. So what are these losses actually doing? It's important because you don't need a loss that doesn't do anything for sure. So these are the most important things that you have to care about when you're training the network, such kind of networks at least. It's how you tell the network if it did a good job. And the reference loss, we notice it increases frame by frame quality, but it has no impact on how well it does temporally, or very little at least. The gradient loss helps with a little better convergence. We gain around 20, 50 epochs in the convergence time. And finally, the temporal loss. It dramatically improves the temporal stability. So let's see how that works. So here you see an example with low temporal loss, and you see it flickers a bit all around. And here you have an example with high temporal loss. And you can see it's way smoother. It still wobbles a little bit. I mean, you have to remember the input is very noisy, but it's significantly better. I can still show you maybe the previous one again. So this is how much it flickers. And the next. So of course, it's a situation where you have a lot of disocclusions and occlusions, so you still have some amount of it. And it's significantly attenuated here. So that was the point for carefully choosing your losses. Now let's see our results. So again, we only using 640 by 480, and we are comparing against variance clipping TAA, and you can see all the videos in the supplemental again. So we just have some images. So on the left you can see the reference, and on the right the input. So they have been resized higher so that you can see it well here. You can still see the input is quite aggressively aliased. And here's our output on the right. And here's VCTAA. And you can notice there's a few artifacts that appear because this frame is actually taken during a motion, and this is a lot of ghosting that you see there. And here's our output against VCTAA. And maybe you're more interested in looking at close-ups. So here on the left you can see ours and VCTAA just next. So hopefully you can see how the shadows, and at least the light in between the shadows, is correctly resolved by our technique. And in VCTAA struggles there, and it otherwise struggles on the lights. You can see that the red has almost disappeared on the behind the railing, where it's still a little present, and the white of the light is still quite present. So obviously I'm talking about temporal antialiasing and I'm not showing you a video, so that's annoying, but it's coming soon. But first we're going to talk about timings and our terrible Catmull Raman interpolation that we're performing. That's the thing that allows you to reproject. It did not exist in TensorFlow, so we have to code it ourselves, and all of this was coded on TensorFlow and the Python implementation. It allowed us to have a lot of variations of networks. But then we had to sacrifice a lot of performance for that. The column mix operation was also performed by us, and it's a CUDA kernel would dramatically 10x this thing quite easily. And the Catmull Raman interpolation, I'm pretty sure most of you know that there is a brilliant new way to compute it with only 4 bilinear fetches, which is really great. And you can definitely get 2 orders of magnitude on this reprojection. But for what results? So I'm going to show you a video of this lampshade there, as you can see on the top of the table, zoomed in so that you can clearly see how the network resolves the lampshade, because it's a thin geometry, which is relatively far away. It's hard to resolve because it's at the limit of how the pixel size. And here it is. So I'm going to show you a few times because it's a very short extract. You can see on the bottom the target. So it resolves, of course, very well. On the top right, the VCTAA, which is quite blurry. And we can see that we noticeably resolve the lampshade, but also the slats in behind, the thing that blocks the sun. They are significantly less aliased than the VCTAA version. And you can obviously see this and significantly more in our supplemental and our paper. So thank you for your attention.
I think we still have a few minutes, or yeah? Okay, so let's do a couple of questions. I don't know where is the cube. Where's the cube? Oh, all right. So does anyone have a question?
Hello. Have you tried to, for the 5x5, to use like a separable one instead? So like a 5x1 and then 1x5?
You mean for performance?
Yeah.
I know that the separable kernels come with the restriction of the rank of your operation, and to be honest, I didn't try. But I was wondering that it would probably lead to a loss of generality in the network. But that would be a good thing to try, because it's definitely significantly faster, especially for the scaling. But just as I said, here, the scaling is not too much of an issue here. So, of course, for our terrible Catmull-Roman interpolation.
Thank you.
Any other question? Oh, I see one there. You can try. Want to try? Yeah. I can do otherwise. I trained. Yeah.
Oh,
awesome.
Good throw. Hi, thanks. So I have a question. So in your results, you only compare it to one other method, which is, I think, not learning based. Did you maybe internally, like in your research group, also compare to, for example, DLSS and XESS, so other AI?
Yeah, so it's interesting because these methods are doing super sampling, which is slightly different. So they're taking a lower resolution frame and expanding it. So of course, if you resize it again, it's kind of an anti-aliasing. But due to many constraints that we had with our dataset and how we built the network, we had trouble implementing it. So it would have been a very good comparison for sure, and maybe even more interesting on DLAA, which is the NVIDIA equivalent.
Hi, have you tried this with particle effects or things that have transparency, no depth?
You mean small dots that move around very quickly?
Glass or anything?
Yeah, so this kind of method relies on motion vectors. And if you can get good motion vectors for that, it's going to work. If you're not getting good motion vectors, it's not going to work. And it's mostly down to that. And getting good motion vectors is definitely still an area of research.
Thanks.
That's it. Maybe I can have a last question. Yeah? Well, no, sorry. No, so I was wondering if you also looked into dimensionality reduction, because you basically always keep the same dimension of your input throughout, right? So you never decrease the 2D dimension, and you also not increase the channel dimension, which is kind of common when you see traditional CNNs, also like UNets or any generative one, tend to do this dimensionality reduction and then upscaling it again.
So you're asking if we tried that? Yeah, we definitely tried it. And what we mostly noticed is that it introduces a lot of a dependency in the network, because while you're resizing and then processing on other sized inputs, it's a lot of time. It's necessarily a sequential algorithm that you're doing there, and that's quite bad for performance. So we tried it. We didn't get through to get, first of all, good results. The results were not super satisfactory. And we didn't notice a very big interest there. Maybe someone can implement it better than us, though.
All right. Oh, interesting. Yeah, I think that's it. Another round of applause for Killian.